Welcome to a new topic for Extension 2 Mathematics. Integration is something that we've dealt with in advanced maths, and then we've seen further integration in Extension 1, and this is even further integration. So we might actually call it even further integration for Extension 2. Let's jump into our first lesson for this topic, which is integration by substitution. Now, in the Extension 1 course, whenever you have to perform a substitution, that substitution is given to you. However, I've encouraged you to try and identify the substitution yourself because that's exactly what you have to do in Extension 2 Mathematics. You may be given an integral, such as this, and asked to solve it. So, looking at this, what do you think would be an appropriate substitution? Well, I suppose we have three options to consider. We could make the substitution u equals 4x. We could make the substitution u equals the square root of 2x squared plus 1. Or we could make the substitution u equals 2x squared plus 1. Which of these do you think would help us the most? If we did u equals 4x, the derivative is just 4. That's not really going to help us with this function down the bottom. So we can rule this substitution out. What about u equals the square root of 2x squared plus 1? In working out the derivative, we would have to apply the chain rule. And so we can see that the derivative will involve a 4x component when this comes out the front. And the fact that this is a power of a half, when we drop the power of 1, that gives us minus a half. So it puts the square root of 2x squared plus 1 on the bottom. So this one looks promising. And likewise with this one, the derivative is 4x, and we have a 4x up there. And then we still have this 2x squared plus 1 down the bottom. So we'd have like a square root of u. So this one looks promising as well. So we might actually do this integral for our first example, and we'll explore both methods and see which one we like best. Okay, so for our first substitution, we will set u simply equal to 2x squared plus 1. And so if we do that, the derivative of u with respect to x is 4x. That means that 4x dx can be replaced with du. And that's nice because we have 4x dx in the original question. So our original integral can be rewritten as 1 over the square root of u, since 2x squared plus 1 is u, and then du, because we've replaced 4x dx with du. Rewriting our integral as u to the power of negative 1/2 makes it even easier for us to perform the integration process. We raise the power by 1, so that'll go to 1/2, and we put it over 1/2, so 1 over 1/2 is 2. And because it's indefinite, we have our constant of integration. Now, u was just a variable that we substituted in, so we'll get rid of that. And 1/2 is actually, a power of 1/2 is just a square root, and so we go back to this. And that's our final answer. Let's have a go at this question now with the other substitution, where instead of just 2x squared plus 1, we're going to let u equal the square root of 2x squared plus 1. Now, this just makes our initial derivative here a little bit trickier, but not by much. Right? We know that this can actually be expressed all to the power of 1/2. So applying the chain rule, half comes out the front, the inner derivative comes out the front, and then we are left with 2x squared plus 1 to the power of -1/2. Now, thinking about what we want in the original question, let's just bring that back up. We want a 4x dx, and we want this square root function on the bottom. So we've already got a 4x, and when we take into account this negative power, we do actually have this square root function on the bottom. So that's really good. We've got this half though, so we don't really want that. So let's multiply both sides by 2, so that we'll get a 2 over here, and then the half will disappear. And let's also take this dx and multiply it to the right hand side. And so we are left with 2 du equals this function. And that's actually the whole integral. So even though there's a bit more work in this part, it simplifies really nicely. We can replace our original integral with the integral 2 du. And so what does that become? Well, the integral of 2 is simply 2u. We have our constant on the end, but replacing u with the square root of 2x squared plus 1 gives us the answer that we got before. So either substitution is fine, substitution number 1 or substitution number 2, and both have their positives and negatives. All right, that's our first example done. Let's do another example. Find the integral of sine root x all over root x. Now, before we start, I shouldn't have to say this, but I will just in case. Please don't think that you can cancel the square root of x on the top with the square root of x on the bottom, because this is one complete function, sine of the square root of x. Anyway, what do you think would be an appropriate substitution? The best one, from the looks of it, would be u equals the square root of x. So, du dx, thinking of the square root of x as x to the power of 1/2, we get 1/2 x to the power of -1/2, or 1 over 2 root x. Now, looking at what we have in our original integral, we have a root x on the bottom, which is good, but not a 2. So let's multiply both sides by 2. We'll keep the du here, and then we have 1 on root x, and we'll move this dx over to the right hand side. So we've still got this sine, and now we'll say sine of u. But then the dx and the 1 on root x, that can be completely replaced by 2 du. And since 2 is just a constant, let's put it out the front. So now we just have to figure out the integral of sine u. And the integral of sine is negative cos. And so we get negative 2 cos u, plus our constant of integration. And finally, if we replace u with root x, we have our final answer. Now, because of the fact that when we derive sine, we get cos, and when we integrate sine, we get negative cos, and the same for all the different trigonometric functions, when we see relatively complex looking integrals involving trigonometric functions, it's actually usually a pretty simple substitution that allows us to form a more standard looking integral. So let's take example 3 as one such integral that looks pretty hectic at first. But if we perform an appropriate substitution, have a little think yourself. What do you think would be the best substitution? Now keep in mind what the derivative of sine x is and the derivative of cos x. And also we've got this sine x all to the power of 9 here. So this looks like the best one to use. So if we use this substitution, well, the derivative of sine is simply cos. And so cos x dx can just be replaced with du. And sine x, well, that's u, so we have u to the power of 9 du. Awesome. This is now something very easy for us to integrate. And then substituting back, instead of u to the power of 10, we have sine x to the power of 10. Nice. Remember, as always, you can look at your final answer and derive it and see if you end up with the original integral. So, trig integrals, piece of cake, right? Until we see something like this. Find the integral between 0 and pi and 4 of cos squared 2x. Okay, so let's just review a few things first that we've seen with our trigonometric identities in extension 1. So first of all, we are going to start with cos of 2x, so the double angle for cos. Now, this is utilizing the fact that cos 2x is cos of x plus x, right? So this is how we originally proved this. But going straight to the result, cos of 2x is cos squared x minus sine squared x. And remember that we can always interchange between sine squared and cos squared using the Pythagorean trig identity. Sine squared plus cos squared equals 1. And so therefore we can say that sine squared is actually 1 minus cos squared, or the other way round, cos squared is 1 minus sine squared. Okay, so using this, let's go and rearrange this first line. And we will start by getting rid of cos squared x. So let's replace that with 1 minus sine squared. And so collecting like terms, we have 1 minus 2 lots of sine squared x. And so if we made sine squared the subject of this equation, what do we get? Well, we've moved this 2 sine squared over to the left. So then we'll subtract the cos 2x from both sides. But then we don't want 2 sine squared x, so we need to halve both sides. And so we get this expression. And in the same way, we can come up with an expression for cos squared x. So starting off with the same line as before, but this time we will replace sine squared with 1 minus cos squared. And so collecting like terms, we have this negative and this negative making it positive. So we have 2 lots of cos squared x minus 1. And when we make cos squared x the subject, we get 1/2 out the front of 1 plus cos 2x. And so this is another identity for us to use. Now we can also extend these identities. So what do I mean by that? Well, notice in the original question that we will get to eventually, it's not just cos squared of x, but rather cos squared of 2x. So let's look at these 2 expressions that we've come up with. Notice that when it's sine squared of x, we have the double angle cos 2x. So if we were interested in sine squared of 2x, this expression remains the same, except that we need to double our angle in here as well. So this would be cos of 4x. Right, so whatever's attached here is always double what we see over here. And so likewise, we could go again if we had sine squared of 3x. What would that give us? 1/2 times 1 minus cos 6x. And the same for cos squared x. And so for our problem, we can replace cos squared of 2x with this expression here. So let's go ahead and finally evaluate this integral. Now, since the 1/2 is a constant, let's bring that out the front of our entire integral. And we keep our limits the same in this type of substitution because we are still dealing with x. So inside we have 1 plus cos of 4x dx. Evaluating the integral, the 1 just becomes an x, and the cos x, or cos 4x I should say, we need to deal with that 4, so we have 1/4, the integral of cos is sine, and then we still have 4x. This is evaluated between 0 and pi on 4. So let's substitute in pi on 4 first. X becomes pi on 4 plus, now what's going to happen when we substitute in pi on 4 here? Well, 4 lots of pi on 4, that's just pi. And if we think about the sine graph, sine of pi is just 0. So that's nice. And then subtracting what we get when we substitute in 0, well, x equals 0, and then sine of 0 is also 0. And so this one simplifies really nicely down to pi on 8. All right, ready for another one? So example 5, which will be the last example for this video, is the integral of 1 over 1 plus root x all squared times root x. And this is a definite integral between 1 and 4. So I've got a few potential options for our substitution. We might like u to simply equal root x, potentially. That's one that you might like to try. It works out okay. You might also think about u being 1 plus root x all squared, but that's not so nice. The one we're going to go with is u just equal to 1 plus root x. So let's use this substitution. What's the derivative to u dx? Well, the 1, that goes to 0, and x to the power of 1/2. So the half comes out the front, so we have 1/2. and then we will have x to the power of negative a half. So that means the square root of x goes to the bottom. Now comparing that with our original integral, we have a 1 on root x. So if we multiply both sides by 2 and also move the dx over to the right hand side, we get this, meaning we can replace the 1 over root x dx with 2 du. But remember, when we are doing substitutions and we're dealing with definite integrals, we need to alter these limits as well, the lower bound and the upper bound. So let's start with x equal to 4. So when x equals 4, what does u equal? Well, we have said that u is 1 plus the square root of x. So square root of 4 is 2, and when we add on 1, we get 3. And also, when we substitute in x equals 1, we get the square root of 1 is 1 plus 1. That gives us 2. So we need to update our lower and upper bounds as well. So we have now the integral between 2 and 3. We have 1 over u squared, right? So this whole thing, 1 plus root x, that's what we've called u. So we have u squared. And the 1 over root x dx, well, that's been replaced with 2 du. So I'm going to put the constant out the front again, like we've done previously. And now we simply have this integral, which looks so much nicer. So 1 on u squared, that's just u to the minus 2. Plus 1 to the power gives us minus 1 over the power. And here are our lower and upper bounds. Might just make this look a little bit better. The minus 1, let's actually bring that out the front. And u to the power of minus 1, well, that's 1 on u. Okay, so last thing to do is just to apply the fundamental theorem of calculus. We have 1/3 minus 1/2. And so when we combine those two fractions together, along with the minus 2 that's out the front, we get a final answer of 1/3. All right, so that finishes off example 5. Like I said, that's the last example for this video, but we're not actually done with all our theory for the first exercise. So stay tuned for the next video.